All right. So one of the last topics we'll talk about, binary trees. Well, wait, we actually already talked about binary trees. Is this what I wanted? I lied. It's not binary trees, it's binary search trees. Bad title. But before any of that, I do want to emphasize one thing. You know, you're watching these videos. Be aware that, unlike before in the class, where each video was like one lecture, I'm covering a lot more content than I would typically in a single lecture. Because one, the lectures are longer now than I'm recording them. But two, you don't have a chance to ask questions. And before, I would take my time and explain things when people were asking questions. We don't have that luxury right now. So just be aware that if you're thinking, oh, I'll watch one video, that's the same as one class. It's not. It's going to be a lot more. So take your time with the videos. Chew on it. Make sure you understand. Don't expect to be able to watch them like you were before. Now, the big point here with binary search trees is, pardon me for one moment. Okay. It's going to be a tree, but the tree enables us to do something interesting. Now, if I gave you a big fat book and told you to turn to page 500, are you going to start at page 1 and go, well, no, that's not page 500, and then turn the page? No, that's not page 500, that's page 2 and 3, 4 and 5, 6 and 7. I mean, if you do that, you're effectively kind of doing like a linear search through your book. And I'm willing to bet no one in this room, if I gave you a book, a big fat book, and told you to go to page 500, I'm willing to bet not a single person in this room would start at the beginning and just start turning pages. That's a silly idea. No, what are you going to do? You're going to open the book like halfway, and maybe it's page like 1200. Okay? So imagine you open this book, and you're looking at page 1200. All the pages on this side are less than, all the pages on this side are bigger than 1200. So where are you going to turn? Are you going to search this side of the book for page 500? No, that's silly, because you know 500 can't be over here. So you're going to probably go halfway-ish between the beginning of the book and where you turn to, and maybe you get to page 600, right? And then what are you going to do? Are you going to look over here? No, you're going to keep looking over here because you know 500 is less than 600. And you keep kind of narrowing it down. Now, if you think for a second, let's say my book was 2,400 pages long, and I opened it right in the middle, and I got to page 1200. Think for a second. How many pages did I just eliminate needing to search through? Because I'm in the middle. All the pages over here are bigger than me. All the pages over here are less than me. And I'm looking for 500, but I'm at 1200. There's 1200 pages this way, 1200 pages this way. I don't need to look at these 1200 anymore because I know 500 is not going to be in there because books, the pages are numbered in order. So I effectively eliminated half of the pages. And then if I split it in half again, let me make sure I draw it, just to make sure. I've got 0 to 2400. If I go to page 1200, I suddenly can eliminate all of these. And then maybe I go halfway here, I eyeball it, and I get to page 600. But I'm looking for 500. So there was 1200 pages remaining. But then I go to 600, and then I eliminate half of 1200. So I divided it by 2 again. And then I'm looking for 500. So maybe I go like here, right? There's 600 pages. Maybe you go to page 300. Well, okay, now 500 is going to be bigger than 300. So I can eliminate these, though, because there's no sense searching through page 0 to 300 for page 500. Then maybe I go to like 450. Keep splitting it in half every time. Well, no need to go there. 525. Well, don't need to go there. And so on and so on and so on. I keep narrowing down search. And every time I do that, I'm like throwing away half of the things I need to search. Where if I started at the beginning and I were to go, okay, page 0, page 1, page 2, page 3, page 4, and so on, it's going to take ages to get to page 500. So we're going to learn about binary search trees. Binary search trees are just trees. It's just a data structure. And we're going to look at an incomplete implementation of a binary search tree because you're going to learn a lot more about this next year. So also we're going to see how we can use a binary search tree to build an ordered list. Or if you were still working on assignment 3, how you could use it to create an interesting priority queue. Okay, a binary search tree. A binary search tree is a binary tree that has a very, very special set of rules that go with it. It's very simple. The rules are, 1, all values, I'll erase this so I can draw an example of what I mean. I've got a tree. It's going to be a binary tree, and my root has the value x. Okay? And of course, my binary tree will have 2 subtrees. Arbitrarily large, who cares, whatever. I'm just going to draw it like this. But the rule is, all values to the left of my root are going to be less than x. That's half the rules. And all the values on the right are going to be greater than, all the nodes, they're all going to be greater than x. If this, of course, would not allow duplicates, a simple fix would to do something like that. Now we can have duplicates. But the point is, for any given tree, the root is x, all values in the left subtree, not just the root of the subtree, all values in that subtree must be less than x. And all the values in the right subtree must be greater than or equal to, if we allow duplicates, they must be greater than or equal to x. Again, not just the root, all the values. But this property must hold for all subtrees that exist in this tree. So, if in here we had a y, all values in this one subtree must be less than y, and all values in this subtree must be greater than y. And if we know y must be less than x, then these must always all be less than x as well. And of course, I drew less than. That should be a greater than. There. Solved. So this definition doesn't allow duplicates, but of course we could add duplicates, which I did by saying greater than or equal to. So, is this a binary search tree? No. Why? Well, the rule was all values on the left must be less than, and all values on the right must be greater than for all subtrees. So I mean, 15, 11, and 16 are greater than 10, so we're okay there. But 15, see how that 16 is in the left subtree of 15? 16 shouldn't be there. 16 should have been on the right, in the right subtree of 15. This one, I believe this is a binary search tree. All values, all subtrees follow the property. So I think we're okay there. Now, here's a quick thing. Look at the leftmost node. Now, the leftmost node, that means go to the left subtree, go to the left subtree, go to the left subtree until we can't anymore. The leftmost node must be what? The smallest value that exists in the tree, the binary search tree. And similarly, the rightmost node, then if we go, I keep losing my marker. If we keep going to the right, go to the right, go to the right, go to the right. Notice, in this case, it would be 15. 15 is the rightmost because we have less subtrees on 15. And even though, 12 is on the right of the 11, 12 is still on the left of 15. So 15 is going to be the biggest one. So a binary search tree is a special case of a binary tree. we still will have all of the operations that a binary tree has, but there's going to be special, more specific things. So we might want inheritance, of course. We'll have a few special operators like add. Now add needs to enforce a rule, just like how add with an ordered list had the rule where, well, when we add something to the list, it must be added in the place that preserves the ordering of that list. It's going to be the same idea for a binary search tree. When we add something, it must follow the property that it's in the right spot on the tree. We'll look at some examples. Insert needs to happen such that the ordering is preserved. And remove also must maintain the ordering, just like an ordered list. When we remove something, the order has to be preserved. Now with the list, it was kind of easy, because if anything, you have a linear data structure. If I remove any of these things and just take it out, the ordering is obviously going to be preserved. But with a binary search tree, with trees, it's going to get a little hairy. Remove max and remove min might be two things we like for our binary search tree as well. For whatever reason, we might like these ideas. They'll become handy for our ordered list implementation. But more on that a little later. Some of these things we can implement today. Some of these things we'll talk about, but they're going to be a little complex, and they're going to be an issue for next semester, or next year. Now, with the example I showed you at the very beginning, turning through the pages of the book, the binary search tree enables us to do a quick search through our tree. It gives us a really cool, fancy way of searching our tree. Now, with a regular binary tree, if we wanted to know if a given element was in the tree, remember what the algorithm was. It was recursive, and the algorithm went like this. This, again, remember, I'm not talking about binary search tree right now, I'm just talking about a binary tree. Searching for something in a binary tree went like this. Look at the current node. Is it null? Okay. Is the current node the thing I'm looking for? If it is, I'm done. If it's not, search the right subtree, left subtree, sorry, this one. And if you find it, great. If not, search the right subtree. And if you find it, great. If not, well, you didn't find it. That's it. Am I it? If I'm not, look over here. If it's not over there, look over there. That's the rule. But take a second and think, what would the binary search tree's search look for? What would the algorithm look like? What would the recursive algorithm look like? And remember, the rule is, all the things over here must be less than me. All the things over here must be greater than me. And if I'm looking for a value, I can change it. I can simplify it quite a bit. I can say, okay, are you the thing I'm looking for? Yes or no? If I am, great, we're done. Also check null. If the thing I'm looking for is less than the current value, which subtree do I want to search? Do I want to look at this side or this side? Obviously, I'm going to look over here. Do I ever need to look over here? No, never. Assuming that the property holds that we do have a binary search tree, there's no way that a value less than me can be over here. If it is, it's not a binary search tree. So, I only need to look over here. And I can do that recursively. So, for example, let's say I'm looking for the value 11. What I would do is this. Is 11 equal to 10? Well, okay, first, does that node exist? Yes. Is 11 equal to 10? No. But is it bigger or less than 10? It's bigger. So I immediately eliminate the left subtree. I don't need to look there. I only need to have one recursive call. I go to the right. Is 15 11? Is it null? Okay, it's less than 15, so go to the left. Is 11 11? Hey, we found it. Now, with the regular binary tree, worst case scenario, I don't find it, I look over here, I don't find it, I look over here. Worst case, for every function call, there was how many recursive calls? 2, in the worst case scenario. Look over here, look over here. But think about the worst case scenario for the binary search tree. How many function calls at most can be called from a single recursive function call? Only one. If I'm less than, look over here. If I'm greater than or equal to, look over here. It can never call both. That's interesting. Yeah. That's funny. I didn't actually know it was going to be look floor 11. I just happened to pick that. Happy accident. So a regular, boring tree. If the tree is not empty, if it is, this, I just said this, search left, search right. What's the computation complexity of this? If there's n nodes in the tree, remember this is a regular binary tree, it's going to be n. You're going to have to look at all n nodes. But, if we go with that modified one that I talked about, it's a little different. It's going to be a lot, let me draw it. I think it's drawn in the slides, but I like using the whiteboard, so bear with me. Okay. What's the computational complexity of this? Before, it was still n. Because if I had a tree that looked like this, is it here? No, I might have to look over here or over here. Is it here? No, I might have to look here or here. Might have to look here or here. Might have to look, well, that doesn't exist, that, and so on. But it's still going to be n. I'm going to have to put my finger on each node. But with a binary search tree, if it's not what I'm looking for, I suddenly cut it in half. Let me put it this way. Let's say there are n nodes in my tree. I go right to the middle. Okay? I can eliminate half of them, such that over here, now I have n over 2 nodes. So this would be like I have my tree. And I'm drawing a nice big full tree to show kind of like a worst case scenario type thing. Also, note the growth of the tree. We already saw this, but I'll say it again. 1, 2, 4, 8. How many would be in the next row? 16, 32, 64, and so on. That's that exponential growth, right? Each time it doubles, but that's with respect to like the height or depth of the tree. Assuming you can see me over there. I don't know if the camera reaches that far. But remember, I care about n, where the n is the number of nodes. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. 15. N is the number of nodes. Okay. So where am I going with this? I go to the middle. I go to page 600. I'm looking for 500. It must be over here. If it's over here, I only need to look at half of the things. Then if I do it again, I'll do n over 2 divided by 2, which is n over 4. And then I keep doing it, n over 8, n over 16. This tree, as we go, no matter where the thing is, bear with me as I draw it out. No matter where the thing is, I know I'm using the example of 600 or whatever, but let's say I have this. I'll have half the nodes over here, half the nodes over here. Really, it should be half minus 1 because of n, but I'm lazy. Then, in this subtree, we have half the nodes, but in this subtree, I've got a quarter of the nodes, a quarter of the nodes. So this n over 2 means how many are in this total subtree? Again, I'm being lazy because really it's n over 2 minus 1 because we don't have that. You'll get way more detail about this next year, but we've got this. No matter where it is, if I have to go this way, if I have to go this way, if I have to go this way, I'm looking for something in this tree. And if the thing's greater than, I go over here. Suddenly I eliminate half the things. I only have half left to look at. Now only a quarter. Now only an eighth. So how many things do I have to look at here? First of all, here, I was like growing by 2s. 2 times 2 times 2 times 2. Every time I went down in that tree, I doubled the number of nodes. But here, I'm not like doubling, I'm like halving. Every time I go over here, I eliminate half the nodes. I eliminate the half the nodes again, then half again. So if this had the relationship of 2 to the n, because we were multiplying every time, now we're dividing some finite number of nodes by 2, by 2, by 2, by 2. If I keep dividing, so when I multiply, I have 2 to the power of n. And you might remember from math class that the relationship here, when dividing, is going to be logarithmic. It's going to be log base 2 of n. The base 2 is important. A lot of times in math, log is usually, we talk about like base 10, but we can have any base. But this and this, which was like 2 to the n, or 2 to the d, where d is depth or height, whatever. It's a similar relationship, but they're like inverses. So this binary search is better. If it was a regular search, I have to look here, look there, I have to look at all n nodes. But because it's a binary search, I look here, and then I only have to look here or here. I get to throw away half the nodes I don't care about, because they're not going to be there. So because every time I look, I'm able to throw away half, throw away half, throw away half, the computational complexity is going to be O log base 2 of n, where n is the number of nodes. Which is really cool. Log base 2 of n is way better than linear. It's better than linear. That's a good thing. We like this. Trees, especially with binary trees, this log, also the exponential, things pop up. Okay, this is just going through an example which I did a bunch of times. Okay, great. And here's what the code will look like. If current's null, well, we didn't find it. If the data at current is the thing I'm looking for, great, we're done. Otherwise, if data is less than the data, if data is less than the thing I'm looking for, do a binary search on the left subtree only. Otherwise, do it on the right subtree. Only need to call it once. And here's the little helper recursive function, where this just calls it on the root. Like if I want to check if my binary search tree contains something, just call binary search on the root, start at the top. Then it just keeps calling the recursive function over and over and over until it finds it or not. Add is really simple. It's going to basically be the same as the binary search, except once we find an empty spot, add it there. That's hard to follow, but I'll show you what I mean with an example. Add. If the tree is empty, insert the new node there. Otherwise, if the tree is not empty, if the data at the root is what we're trying to add, this is a duplicate issue. We could simply change it, go to the right if it's the same. That's usually the convention, by the way. If we're not allowing duplicates, we don't allow duplicates. If we are allowing duplicates, always go to the right subtree. If the data is less than the root, add it to the left subtree. If it's greater than, add it to the right subtree. Let me show you an example. I want to add 13. So what are we going to do? Okay, go to 14. Is 13 less than or greater than 14? It's less than. So go to the left subtree. 8. Is 13 greater than or less than 8? Well, it's greater than. Go to the right. 12. Is 13 greater than or less than 12? It's greater than. Go to the right. Empty tree. It's a subtree, but remember the subtrees are trees. But basically we're over here, so we put it there. Done. See how it's basically the same as the search? But, I mean, all we have to do is now, once we find the empty spot, put it there. It's easy. Now I'm going to show you some code for this, and understand there's literally an infinite number of ways I can code this. I'm just showing you one implementation. What do we say? If cur is null, create a new binary node, with the data in it, that's, okay, put it there. And return it, which means return a pointer to that binary node. That's important. Note that kind of like the base case is returning a pointer to a new node. Then, if data is less than the data I'm looking for, set the currents left to the recursive call and insert. Which, if the recursive call and insert's the base case, well then it's that new node. If it's greater than, same thing. Otherwise, return current. But current is a pointer to a binary node. So, imagine for a second I said, okay, cur set left. And I call the recursive function insert. We have two options. It's either going to be the base case or not the base case. If it's the base case, we return a pointer to, I'll draw it. Because it can be hairy to see what I mean, but I think once we visualize it, it'll help make a lot more sense. Let's say I'm adding it here. It's the node I'm adding. So, this is the base case. I said, okay, is cur null? No, okay. It's less than, it's greater than. I go here. Now we're at that base case. It's null. But I'm creating this new node, and I'm returning a pointer to this node. So I've got some pointer, the memory address of where this node is. Okay? Now, the previous call, I will call the set right. And I called it on insert. And what did that function call return? That insert, which got me to here, which is the base case, returns this pointer. So I'm saying set right to that pointer that I just returned, which is this pointer. Okay, set right will go, boom, to this memory address where this node is. Otherwise, now we're working our way back up. So, okay, we added it, we go back. We called this one because this was from here to here. So now we're done this. And what are we saying? We're returning cur. Well, cur is a pointer to this node. It's the memory address of this node. And I'm returning that memory address. Then I go back up to this one. Okay, so that was like go left. And it sets the left to this pointer, which it was already pointing to, but that's fine. It just basically set your left to the thing that you were originally pointing to. Why? Because. So it's all good. It's hard to explain this without people here to ask questions. So if you're struggling with this, take your time. Remember, there's only one trick in programming. What does the code say? Grab your sheet of paper, your pencil, follow it slowly. Keep track of everything. If you do that, you're still struggling, you're skipping steps. Slow it down. What does the code say? None of this is a mystery. It's code that we've all seen before. We're just using it here. Execute the code slowly, pencil, paper, take your time. And then just, yeah, okay, there's the helper. So, this is just showing an example of the adds, okay? If we remove, this is where things get hairy. Like if I remove 38 from this tree, what do? I can't just delete it because then I lose 31 and 34. I suppose I could move 31 up to where 38 is. I guess that would work. But, I mean, we have a couple of cases. If the thing I'm trying to remove is a leaf node, it's easy. Remove 7, get rid of 7. 7's a leaf node, you get rid of it, there's no real any consequences. Remove it, decrease the size, we're done. But, what if it's an interior node? Like, link from the parent to I think that's supposed to be successor. Like, what if I wanted to remove the root, 26? What do? Okay, I delete 26. Uh-oh. This is hairy. Usually what the trick is, replace it with the node's predecessor from an in-order traversal. But that's too complex for 162. You're going to talk about that next year. Yeah. Outside the scope of this. So, if I remove 70, well, that's easy. That's a leaf node. You're gone. Done. Now, What if I wanted to remove 7? Okay, well that's easy. I could just take, if I remove 7, I can just move the 9 up, right? That's fine. So that's what I do. Now if I remove 38, what do I do? Well, the trick here, a lot of times, again, I just said, what would have been right before it in an inner traversal? Not after, before. You could do after, but I think before is going to be a little easier. So what would come right before 38? Well, that would actually be the rightmost subtree, pardon me, the rightmost node of the left subtree. In this case, 36. So we replace 30, like put the 36 where the 38 is. And the reason we can do that is because I know, because 36 is on this side of the left subtree, it must be less than all the things in the right subtree, right? So I know that if I take this node here, I'm guaranteed that it's going to be less than all the things on the right subtree, which is good because that would preserve the property that everything over here must be greater than 36. But at the same time, we also need to make sure that 36 is bigger than all the things over here. So 36 needs to be less than all the things over here, but bigger than all the things over here. Well, we're covered. Because 36 was in the left subtree, I know it's less than everything in the right subtree. But because 36 is the rightmost part of this subtree, what did we learn before? What is the rightmost node of any tree? It's the biggest thing in that tree. So if we take the rightmost thing of the subtree of the left side, that's going to be the biggest thing in that subtree. So I therefore know that it must be bigger than everything in the left subtree. So that's why we can do that. If you're having a hard time wrapping your head around that one, take your time, you can figure it out. Anyway, just more examples. Remove minimum's not too bad. I mean, if it's the leaf, we just take it out, like 7. But what if, like, okay, so root has no left child. Well, that means the root is the minimum. But what if we want to remove it? So if the root is the minimum, the right subtree's root is now going to be the new root. Because if there is no subtree over here, then the new min must be the top, like, that's going to be the new root. Not the min, the new root. Is the root of the left subtree. But what if the leftmost is a leaf? Well, that's simple, just remove it like a 7. But if it's an interior node, it gets a little hairier. Like if I remove 7, okay, not too bad. We take out 7, 9 gets like promoted. Remove 9, okay. We remove 15, promote the 18, and so on. Remove max, it's going to be similar, but the other way. Find min might be a little easier. The removes are hairy. Don't worry too much about them. You're going to cover them in a lot more detail next year. I said that 1,000 times. I'm just trying to remind you, don't get bogged down by those details. They're interesting, don't get me wrong, but they're not a big focus for you right now. Refine min's easy. I mean, you can do it recursively or iteratively. Go all the way down this subtree until you can't go anymore, you found the minimum. Find the max, go all the way down, keep going to the right, go to the right, go to the right, go to the right until you can't anymore, and then you found the max. That's it. Take a second, pause the video, do the traversals on this tree, which happens to be a binary search tree. If you do, is there anything interesting about any of these traversals? So pause it, see if you can figure it out. Now, the only one that's really interesting is going to be the in-order traversal. And just do it and you'll see. Long story short, it'll print out the things in order. It'll go 3, 8, 9, 12, 14, 19, 23, 26. So we have a very incomplete binary search tree, and next year you'll learn a lot more. So if, for example, we wanted to implement, let's say, okay, before we could implement an ordered list. I think we did it with a linked implementation. And then I think in the lab you did an array implementation of an ordered list. I think. Now, we used a container. array and linked nodes. But we could use a binary search tree as our container, which I realize has binary nodes inside of it, but let's just use a binary search tree. Let's pretend we have a complete binary search tree implementation. We don't, but let's pretend we do. It has add, it has get the size, is empty, has the removes, which I know we didn't implement, but let's pretend they're there and they work properly. Remove min, etc. So with an ordered list, we need to be able to do what? Add things such that the ordering is preserved. Binary search tree might be interesting. We want to be able to move arbitrary things. Get the size, check if it's empty, but that's it. Now, if we had this linked implementation of an ordered list, what's the computational complexity of add? Well, we wanted to add such that the order is preserved. And in order to know where this new thing goes, we're going to have to do a linear search. So the insert is going to be order n. Worst case scenario, it's got to go to the end, and we just got to go, okay, do we put you here, 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 here? Linear search. But the remove is easy. Remove, well, if we're removing the min, it's easy. But if we're removing a specific element, we still have to do a linear search, right? We're still going to have to search through our list to see if that thing exists in it. So the add and remove are going to be linear. Remove min will be constant time because it's always going to be the first thing. But your general purpose add and remove are going to be linear. But if we have this complete implementation of a binary search tree, what's the computational complexity of add? Remember, I want to add this new thing. I look. Do I go over here or over here? If I go over here, I ignore this side of the tree. I eliminate half the things. Asterisk. More on that asterisk in a moment. If it goes over here, we eliminate this half of the tree, asterisk. And we keep eliminating half and half and half and half and half. So at most, it's going to be log n. At most, I mean, how many nodes in here? 1, 2, 3, 4, 5, 6, 7. There's 7 things. But I'm going to have to go down a tree. Pardon me, go down the subtree. So there's 7 nodes. If it was order n, I would have to look at like n different things. But here I would go, okay, just go here, here, maybe it goes here. I wanted to add like 0. And 0 happens to be like, it would be the new smallest thing. So I would go less, less, less. I only had to go 1, 2. I only had to go like 2, maybe 3 down. 1, 2, 3 down to find where it goes, which is way better than 7. And as this tree gets bigger and bigger and bigger, the number of nodes increase. The amount of work, like, I only have to go down very little far. Basically, if I have n nodes, what's the depth of the tree going to be? Basically, what I was asking, I just erased it moments ago. What's the relationship between the depth of the tree and the number of nodes in the tree? We've got that, well, number of nodes is like 2 to the n. Number of nodes, if I know the depth, is like 2 to the depth. Okay. But if I know the depth, it's going to be like log base 2 of n. Now, if I don't know the depth, I want to know the depth. It's going to be log base 2 of n, where n is the number of nodes. I mean, there's this log exponential relationship there. So the depth of the tree is going to be like a logarithmic relationship between the number of nodes in the tree. So I only have to go down to where one of the leaves of the tree will be, which would be like, at most, if it's asterisk, not that far compared to the number of nodes in the tree. Now, let's do a quick comparison. If we implemented this binary search tree as like the container for our ordered list, if we had a linked list implementation, remove first is easy, it's constant time. But a binary search tree, we would have to go to the left, 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 left until we got to a leaf. And that's going to be like log n, log base 2n. Remove last, assuming we don't have a pointer to the end, it's going to be linear. We have to go all the way to the end to get to the last thing and then remove it. But with a binary search tree implementation, we just go to the left, or go to the right, go to the right, go to the right till we find it. That's going to be log n again. A general purpose remove is going to be linear. But a binary search tree one, well, we'll just do a binary search for the thing I'm looking for, where we get to eliminate half every time, and that's going to be log n. Getting the first, order 1. Binary search tree, log n, we got to go all the way to the beginning. But last, n, I mean, we could start to see how a binary search tree, you start to win quite a bit if you use a binary search tree as your implementation for an ordered list. I fear that I'm going a little too quickly at talking about the relationship between the depth of the tree and the number of nodes in the tree. So I want you to make sure you take some time and convince yourself that that's the relationship. Grab a sheet of paper and a pencil, draw out a tree, count the number of nodes in the tree, count the depth of the tree, and see if you can find that relationship using those operators. Basically, if I have if the depth of my tree is 0, and n. If the depth of my tree is 0, how many nodes do I have? Remember, when the depth is 0, that's when it's just the root. Okay. If depth is 1, I'd have 1 plus 2 more. So 3. If it's now 2, I've got 4 plus the 3. 2, 4, 5, 6, 7 total. If it's 3, so we added the 4, now we need to add 8 to this, so that's 15. 4, now we need to add 16, so it's going to be 31. Right, so here I added 2. So here to here I added 2, here to here I added 4, here to here I added 8, here to here I added 16. If I were to go again, I would add 32, which would bring up to 63. Right? Let me see if you can actually see this. Oh yeah, you can see. Right? Now, what is 2 to the 0? That's 1, right? 2 to the 0 equals 1. What's 2 to the 1? Well, that's 2. 2 to the 2, well, that's 4. So, I mean, it's not quite perfect. In fact, I think we might have to modify this a little bit. And some of you might remember from last semester when we were kind of playing these games to try to find the relationships between certain values. I think the relationships, I'm going to try another one. What if it's like 2 to the d plus 1 minus 1? Bear with me, let's see if this is right. So 2 to the d plus 1, well d plus 1 would be 1, that would be 2 minus 1, okay, that's 1. So 0 plus 1 is 1, 2 to the 1 is 2, minus 1 is 1. So now 2 to the 2 minus 1, that's 4, okay, that's 3. 2 to the 3, so 2 to the 2 plus 1. Should do this, 1 plus 1. 2 plus 1 minus 1. So 2 to the 3 is 2 times 2, 2, okay, that's 2. 4, 8 minus 1, 7. So it looks like the relationship here is going to be 2 to the d plus 1 minus 1. That's that exponential relationship between the height and the number of nodes. And if we do the inverse, where we do the log, base 2, we will find the similar relationship between the number of nodes and the depth. Just when you see exponential, the inverse is the log, and vice versa. So that means like the height of a tree, asterisk, I'm going to talk about the asterisk in a moment. Some of you might be able to, you may have been asking questions about like, but hold on, and if you have, cool, if not, don't worry, I'll show you. Point is, the number of nodes and the depth, basically, if I'm finding the minimum, the most I'm going to have to go down is the depth of the tree. And the depth of the tree has this logarithmic relationship between the number of nodes in the tree. That's what I'm trying to say. If you don't believe me, grab your sheet of paper and a pencil, scratch it out, convince yourself. It's important. These types of relationships are things I love to ask on exams and whatnot. Okay, here's where the asterisk comes out. A balanced tree has a very important property that we love. If trees aren't balanced, we might run into a bit of a problem. But the idea is, a balanced tree has the property that for any node in the tree, the height of its leaf, or pardon me, the height of its left and right subtrees can differ by at most 1. Remember that the height of an empty tree is -1. Basically what I mean is, here, it's balanced. Because for every subtree in that tree, the height difference is at most 1. The height difference of the left subtree is 1, 2, like, it's at most 1. But on the right, we're in trouble. Because the left subtree has a height of like -1, and the right subtree has a height of 1, 2. So, the one on the right is not balanced. Basically, we want a similar-ish number of nodes on each side. That's the idea. And that's important. So, why is this balanced? Why do we care that they're balanced? Well, let's pretend I've got a binary search tree implementation. And then I add these numbers. I add 3, then 5, then 9, then 12, then 18, and 20. In that order. Let's see what would happen. Okay, I've got an empty tree. Yeah. I've got an empty tree, so I want to add 3. Where does it go? Well, it's the root now. Now I want to add 5. Okay, is 5 greater than or less than 3? Well, it's greater than, so we put it on the right. 9. Is 9 greater than or less than 3? Well, it's greater than, so we go to the right. Is 9 greater than or less than 5? Well, it's greater than, so we go to the right. Okay, so it goes to the right. 12. Where does that go? We go to the right, go to the right, go to the right. Okay, so it's on the right of 9. And so on, and so on. This tree is obviously not very balanced. And this tree might remind you of a data structure we've seen before. To me, this doesn't look like a tree, does it? What does it look like? It looks more like a list. Now, if I asked you, with a balanced tree, remember there's an asterisk next to these things, with a balanced tree, if I wanted to find the maximum, it's just go to the right till you can't go anymore. And if the tree is balanced, we've got this property. Remember, we want about the same number of nodes on each side of the tree. So we've got this property of number of nodes, depth, this is like logarithmic exponential relationship. If number of nodes is n and we're going down, go to the right, go to the right, go to the right, well the depth of the tree, if it's balanced, is going to be like on the order of log base 2 of n, which is way better than linear. But this tree is not balanced. And if I got to go to the right, go to the right, go to the right, what's the complexity of this? It's going to be linear. Find the biggest number, go to the right, go to the right, go to the right. The relationship has nothing to do with log anymore because this tree is not balanced. We call these degenerate trees. Yeah, okay. Okay, self-balancing trees. You'll learn about these next year, I'm pretty sure. You'll learn about like red, black trees and AVL trees are the popular ones, and perhaps AVL is more popular, but don't quote me on that. And you'll learn about trees that, let's say you started adding things like I was doing, where it kept going that way. We can make a special type of binary tree that if you start to add, and your tree starts to become degenerate, it'll self-balance itself so it doesn't, which is pretty good. So that's it for the binary trees. Now let's move on to sorting. So a bunch of this is going to be review for those of you that took 161, but for those of you that didn't with me, some of this is going to be new. I'm not sure if you covered this in the engineering section of 161. Maybe you did. If you did, great. If not, that's fine. Sorting is very important. This is one of the more important topics of 162. And it's unfortunate that I saved it to the end and we're stuck in the situation we are. But here we are. There's going to be some concepts I'm going to just basically skip. It's going to be more the heavy-duty computational complexity analysis stuff. I'm going to skip it because that part, I suppose, is not overly important for 162. It's too bad. I would encourage you to go over it yourself, see if you can make sense of it. If not, don't worry too much. Computational complexity of these sorts are important to understand, but I'll point it out as we go where things start to get kind of like a little overkill for us right now. You'll see. Basically, when you see the K's pop up, you can, I'm just going to skip it. You'll see. I'm just going to make sure I've got a nice clear board, because I like to draw, and who knows. We're going to start by covering some of the simpler sorts. And it's funny to kind of talk about sorting as this really important concept, because I'm willing to bet every single person in this room, I would bet $1 billion that everyone in this room at some point in their life has had to sort something. And whether you realize it or not, you would have executed some algorithm to sort the things you're sorting. And it almost seems overkill to formally define and show you sorting algorithms, because you all know how to do it. And I'm actually willing to bet that some of the sorting algorithms that I'm going to show you today, the ones you've been doing on your own when having to sort things, have been some funny bastardizations of the ones you're going to see today. So a lot of these you're going to be familiar with. And they might seem corny and silly, but understanding sorting is really important, because sorting is some of the first algorithms you get to look at. And then you also get to look at better ones. I'm going to also show you that the sorting algorithms you've probably been using are crap. I hate to tell you, you're really bad at sorting things. And I'm going to show you good ways to sort things. Hopefully it blows your mind and you get excited. But anyways, I'll leave this up, it might be handy. So we're going to look at some sorting. Okay, great. Why sorting? It's a classic problem we take for granted. We've all sorted things. Turns out you suck at it. Newer sorting algorithms come up every once in a while. It's cool. Which is weird to think. I can imagine cave people were sorting things. Maybe they were sorting bones or something. I don't know. But people have been sorting things for millennia. And turns out they probably sucked at it. And it actually wasn't even until not that long ago, freakishly not that long ago, that we discovered, oh, we suck at sorting. Here's a better way to do it. Anyways. So why sorting? How many of you, yeah, okay. How many sorting algorithms are there? A lot. The list goes on. Anyways, sorting. Are some better than others? Yes. For others, sometimes. If you go to this link, you'll see some interesting visualization of some sorting. So we're going to talk about bubble sort. Bubble sort is very simple. This might be a sorting algorithm you've used. Chances are, too, usually what I would like to do in one of these lectures is that I let people talk to each other for a couple minutes, and they try to come up with, okay, formalize some of the sorting algorithms you've done. And a lot of people will come up with this one, or at least part of this one. But the idea is, do a pass on the list. Let's say we have a list of things we want to sort. Do a pass. And as I do a pass, I'm going to compare neighboring elements. If the neighboring elements are in order, leave them alone. And then go to the next two. If they're out of order, swap them. Then go to the next two. If they're in order, leave them. If they're not, swap them. And so on and so on and so on. And you have to keep doing this over and over and over again until it's sorted. So here's a little visualization. I've stole this from Wikipedia. Compare these two. They're out of order. So we swap them. Great. Now move to the next two. Compare them. Out of order, swap them. Now, a lot of people, when they come up with this one, they forget that they need to do this over and over again. Because look, 5 and 3 are out of order. Swap them. 6 and 1, okay. 6 and 8, they're in order, we leave them alone. Now we're going to have 8 and 7. We got to swap them, because they're out of order. Yeah, 8 and 2, out of order, have to swap them. Now, also, notice after one pass, what's going to be in the last index after one pass? The last index it must contain the largest element, if you did everything right. So, based on that, I know that I don't need to go all the way to the end anymore. I never need to compare anything to 8 anymore, because I know nothing can be bigger than 8, which is interesting. But I keep doing this over and over and over again. So, let's think about the computation complexity here. Without even looking at the code, because I know when we look at code, we like to cheat and look at the loops, right? But, okay, we got to think worst case scenario. Okay, we have to do a pass, and we have to do a pass some number of times. Okay, so what's the computation complexity of doing one pass? Well, we got to look at all the things. So computation complexity of one pass is n. One pass is order n. But how many times do we have to do this order n thing? Well, I mean, from this, you might be able to figure it out, but I'll just tell you. But if you'd like a chance to figure it out, pause the video, see if you can kind of see, at most, how many passes am I going to have to do. And you'll see, if after one pass, I know the biggest thing's in the last spot. If after the second pass, I know the second biggest thing is in the second last spot. So if I have n things, after one pass, the largest one's there, then the next one, then the next one, then the next one. If every time I do a pass, I eliminate I know one thing's in its proper position, I'm going to have to do n passes. So I have to do n work n times. Right? So that's going to be n squared. Now, some of you might be saying, well, hold on a second. And what I'm about to show you is a bit of a trick. But this is not formal, this is not rigorous. But I like it because it helps visualize things. The first time I do a pass, it's going to be order n, right? I've got to compare all n things, right? So let's say I've got n. The first time I do a pass, I have to compare all n things, right? But of course, after one pass, I know that I've got one less thing I need to compare, because I know 8's in the right spot. So really I don't need to compare n things, I need to compare n minus 1 things. So the second pass, so this will go to n. This is n minus 1. So it's less work the second time. And then the third time, it's going to be n minus 2. And then n minus 3, and so on. Every time I go down, if I go to n, I only really have like one thing left. So I'm actually reducing the amount of work. But how much work is being done here in total? Well, take a second and think of this visualization. If I were to draw this again, kind of as a square, this is n, and this is n. The square would kind of be like that, right? Where this is the amount of work being done. First time I got to do n minus 1, n minus 2, every time I go down, I've got a little bit less work. We got a square here. If we had to do n every time, we know it's going to be n squared. But how much work is this? Well, to me it looks like half a square. N over 2 amount of work. But of course, that's just like a coefficient. 1/2 times n, there we go. It's still n squared. I'm also going to show you something else. And this is perhaps a bit of a tangent, but it's important. A lot of people, okay, let me put it this way. Let's think backwards. How much work is being done this time? 1. And then how much work am I doing the next time? Well, it would be 2, right? Because here I was removing. Now I'm going to add 1. So the total amount of work is going to be 1 plus 2 plus 3 plus n minus 1 plus n, right? Because 1, 2, 3, n minus 1, n. That's the total amount of work being done. So this right here, total amount of work being done. Now, does this look familiar to everybody? It should. You've probably covered it in your math classes in university. And if not, I'm pretty sure you covered this in like grade 11 or 10 math or something. But this is what we call like an arithmetic series. And for anyone here, if you can remember like the equation to know what the arithmetic series is, well, it's going to be n times n minus 1 divided by 2. Or is it plus 1? I think that's better. That's just like the little equation or a little expression we use to calculate what the sum of this series is. If you don't remember this though, here's my tangent. I love talking about this because I love pointing out bad math teachers. Bad math teachers will show you this and be like, here, just know this. Know the fact that, if you add all these things up, This is the equation that would tell you what the sum of all these things is. Let's test it. If I did like 1 to 5, 1 plus 2 plus 3 plus 4 plus 5, what is that? 5, okay, 1, 3, 6, 10, 15. But let's plug it in that equation. So that's going to be 5 times, what is that? 5, 6, what's 6, 30, what? 5 times 6 divided by 2, that equals 30 divided by 2, that equals 15. It checks out for this example at least. So we're happy. Now, this is a magical mathematical expression that tells you what the sum of this series is. And I'm going to tell you right now that if I put you in the hot seat, and this is the $1 million question, you know, you're on some game show and this is the question they ask you. And you can't remember this. You can't remember. But the question comes and they ask you, what is, pardon, it's not the $1 million question, it's the $1 trillion question. This is the most important question of your life. They ask you, what is the expression to tell you what the sum of these things are? I'm willing to bet you could derive it. I'm going to show you how you can derive it yourself. Remember, math was not handed down by the gods on golden tablets for you to know. Math was kind of like discovered by people like you and me. And I'm going to show you how you can kind of rediscover, reinvent this expression. Okay. Here's what I'm going to do. I want to know what the sum of this is. But I'm going to show you a bit of a trick. I'm going to, so I've got 1 plus 2 plus 3 plus 4 plus 5 plus blah, 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 plus n minus 1 plus n. Okay. I want to know what that is. Here's the trick. And this is the one thing you got to remember. And after this, you should be able to figure it out. I'm going to double this series. I'm going to double it. So I'm going to remember that I times 2 this series. And by doubling it, I'm going to write it again. 1 plus 2 plus 3 plus n minus 1 plus n. I doubled it. Why? Because. But would you agree that if I took this value, if I knew the answer to this, and I doubled it, I would also get this plus this. Obviously, that's how basic math works. Okay, great. But this doesn't help me. You're right. I mean, it kind of does, but I'm going to redraw this in a way that you might like a little bit better. I drew it as 1, 2. Here's what I'm going to do. I'm going to do 1 plus 2 plus n minus 2, n minus 1 plus n. There. All I did was I reversed this. Before it was 1 plus 2 plus 3, n minus 1, n. All I did is I just reversed it. 1, 2, blah, 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 blah. Okay? Now I'm going to ask you. I don't want to add this way. I'm only going to do some of the additions. And the additions I'm going to do is this. What is n, and what is n plus 1? Well, that's just n plus 1, right? And what's n minus 1 plus 2? Well, that's n plus 1. What's n minus 2 plus 3? Well, that's just n plus 1. What is 2 plus n minus 1? Well, that's just n plus 1, right? And then what's n plus 1? Well, that's just n plus 1, right? Huh. Well, that's interesting. I've got a whole bunch of n plus 1s. How many n plus 1s do I have? Well, I've got n of them. So this is equivalent to saying n times n plus 1, right? But of course, I had to double this series to get that. So if I doubled it, what do I have to do to undo my doubling? That's it. You could have figured this out. $1 trillion question, you're in the hot seat, pencil and paper, you'd figure it out. You'll never forget it. The trick is double it. And you can remember this. This wasn't handed down by the gods. It wasn't some godly genius who came up with it. It was someone who scratched it up and was like, oh, hey, here's a neat, interesting property with the math. And that's what we like to do in computer science, is play around with that math. Remember, computer science is just a fancy type of math that we're too lazy to do, so we make computers do it for us. Anyways, point is, we have n times n plus 1 divided by 2. What's, if we figure this out, well, that's like n squared plus n squared plus n. Well, do we care about this? Do we care about coefficients? No, this is order n squared. Long story short, there we go. Here's some code. Take your time, go through it. All this is doing is swapping things. We need a third variable to swap. If I have this hand sanitizer and this marker and I want to swap it, I need like a third variable to go. Otherwise I will overwrite one. So I need that third variable. That's all this swapper thing is doing. But all this is doing is saying, for j to n, for I to n minus 1, do the comparison. If they're over, swap them. If not, carry on. And the j, that outside loop, that's the do it n times total. We can actually improve this a little bit, where we just add, already talked about that. We can improve it a little bit, where we just add this little variable, little boolean, to check if things are in order or not. Basically, if I ever do a pass, and I never swap anything, then I know that my list is sorted. For example, if I gave you the list 1, 2, 3, 4, and I told you to do bubble sort, I don't need to do this n squared times. I could go, okay, no swap, no swap, no swap. Oh, I did a pass and there was no swaps, therefore the list must have been in order. That's just a little fancy improvement on it. If you don't understand, you will if you take your time, pencil, paper, go through the code. There's no magic here. The only trick is, what does the code say? Don't make any assumptions. Best case scenario is order n, like I just showed you. Worst case is n squared. That would be if the list was in perfect reverse order, then you would definitely have to do it n by n times. Pardon me for a moment where I take off my sweater, get a little toasty in here. Okay, bubble sort, it's not very good. Insertion sort, here's the idea. What if I've got like an already sorted list? I'll have a list that's already sorted. And then I'm going to search through the unsorted list. And every time I add it to the sorted list, I'm going to do this insert such that that list remains sorted. Kind of like I'm inserting new things into an ordered list. We can actually do this fancily. Well, let me restart that. Here we go. Okay, 6. This is my sorted part of my list. So now I'm looking at 5, and I want to add it to that sorted part of the list. Well, that goes before. There we go. So now I want to add that 3. So the black part is the sorted part. So no, it's less than 6, less than 5, must go there. Now look at the 1. I want to add the 1 to the sorted part. So now the first 3 things are sorted. 1, well, it's less than 6, less than 5, less than 3, so we have to move these things down, and there we go. Now 8, we want to insert it. Is it less than 6? No, so it just stays there. 7, is it less than 8? Yes, so we got to move it. Is it less than 6? No, it just goes right there. 2, here's the big long one. No, okay, move it down. Move the 8 where the 2 was, move the 7 where the 8 was, move the 6 where the 7 was, where the 5 where the 6 was, where the 3 where the 5 was. 2's not less than 1, so it goes there. 4, and so on. Here I'm using one array. I could do this with, it's important to note that insertion sort is the idea. I'm adding new things into a list that's sorted. And this new thing, as I add it, must go in this sorted list such that this list remains sorted. It's not the fact that, oh, I've got one array and how the code exactly looks. That's not what's important about insertion sort. Same with bubble sort. The idea of bubble sort was not the code, it was the idea. Do a pass, switch things if they're out of order. Keep doing that until you're done. That's bubble sort. Nothing to do with the code, nothing to do with the array or the data structure I picked. The array, I showed you how to do it with an array. Assuming this is an array. It could have been a list, whatever, who cares? But note that the idea behind the algorithm is actually kind of independent from the code itself. And your choice of data structures, which we will see in a moment, will affect how you code the idea, the high-level idea. Remember, the high-level idea is just insert things into an already sorted list such that the already sorted list remains sorted. That's insertion sort. That's it. How we code it, all that matters is that we're following that idea. I don't care what your code looks like as long as it follows that idea. I don't care what data structure you use as long as you follow that idea. So here's an example of the code. The outside loop, that's the moving down. The inside loop is, okay, I've got a new one. Do I need to shuffle things down to find where it goes? I'm doing this, I did that the wrong way. Should have done it this way. The outside loop is we're moving down the list. Then the inside loop is okay, move this way, it goes here. Take your time with this, understand it. I love sorts, I love putting them on exams. What's the best case scenario? Order n, the list is already sorted, so I never actually have to ever run that inside loop. That would be like, add this to the sorted, okay, it's sorted. Add this to the sorted, oh, no need to shuffle. Add this to the, oh, no need to shuffle. Add this, no need to shuffle. Add this, no need to shuffle. Worst case scenario is if it's in reverse order. So I've got to move down the list, that's order n. But how much work am I doing each time? Well, 5, I shouldn't draw this yet. 4, 3, 2, 1. Do this, I got to move. Then I add this, I got to move it down, move it down. Move it down, move it down, move it down. Move it down, move it down, move it down, move it down. This much, how much work? I got to move it down n. And how many times is the outside loop executing? Remember, the inside loop is the shuffling down. The outside loop will run n times. So it's going to be n squared again. Another horrible sorting algorithm. N squared, no good. Yeah. Okay, insertion sort. We can do this with the stack. Why? Because you might find this a little contrived, but that's kind of the point. The point is to show you how your code would have to change, how the details of your algorithm, the specifics, are going to have to change depending on your choice of data structure. Some data structures are naturally a good idea, some aren't. That's fine. But here's the general idea. And in this example, we're going to skip over some of the analysis part, but it's still going to be n squared. Okay, so what we're going to have is two temporary stacks. One's going to be called temp, and one's going to be called sorted. Where sorted will always have the things in the proper order sorted. Temp is just this temporary one. We'll see how it's used in a moment. They both start empty. The contents of sorted will always be in order, smallest item on the top. Okay, temp will temporarily hold items that need to be shifted around. You'll see in a moment. So, while there are still things to be sorted, so imagine I have this bag of numbers I want to sort. I'm going to switch markers because mine's starting to dry out there. I've got a bag of things I want to sort. 1, 4, 7, 2, 9. Okay, so the thing says, well, there are still things to sort. Okay, fine, I've got that. I'm going to remove an item. Oh, my battery's running low. Oh. See how far I can get before my battery dies. Well, sorted is not empty, and the top of sorted is smaller than the current. So I have sorted and temp. I'm going to have to speed up because my battery's about to die. You know what? For the sake of time, go through this part on your own. It'll make sense. Trust me. Example of it. That's n squared. Okay, great. This is the part, don't waste your time. The insertion sort stack analysis in deep. Whenever you see the case, skip them. Insertion sort stack. Okay. Let me just lower the brightness on my computer. See if we can save a little, get an extra couple more minutes. Insertion sort, okay, great. Selection sort. Repeatedly put particular values into their final position. All I'm going to do, I'm going to scan my collection of things. Find the smallest one. If I have the smallest one, I know where that's going to go in a sorted list. Once I put it there, great. I'm going to scan again. Find the second smallest one. Put it in index 1. Remember, assuming we start at index 0. That's what the smallest one is. Look for the next smallest thing. Put it where it belongs. Look for the next smallest thing. Put it where it belongs. Great, done. Here's an example. 2 is the smallest I've seen so far. Okay, great. Scan. Oh, 3 is now smallest. Switch. Just repeatedly keep scanning. But this algorithm is actually horrible. Best case scenario and worst case scenario. Where the other one's best case scenario order n. Here, best case scenario is n squared. Worst case scenario is n squared. This is actually a really bad one. And the reason is, I need to scan the list n times, right? To find the smallest thing. Because I need to, okay, how much work is it to scan the list? Order n. How many times do I have to scan that list? N times. So it's actually horrible. Don't use this one. Here's the code, look through it, it's in the slides. You can do it with a cube if you want, cool. Again, ignore this part. BOGO, here's a good one. I give you a list of things. You check if it's sorted. How much? No!